The size is 3 by 4 by 10. Anybody want to take a guess what that means as far as size?
3-inch suction.
4-inch discharge.
Flip them. 4-inch suction, 3-inch discharge. You would think you would go in the suction first, right? And the number would be out there. But we're pump people. We can't get anything straight. But anyway, you'll hear it referred to as a 3410, a 4310, so on and so forth. That as in reference to the size. So 4 being the suction, 3 being the discharge. What's the 10 represent? Impeller diameter. Right, impeller diameter. And then this would be the eye of the impeller. If you took the surface area of the impeller and measured it, took all the little curves out of it and everything, you'd have 17.5 square inches of surface area. Has number of vanes. This is a 5 vane. If you went around the outside, 5 vanes. And this is a Francis vane design. And it gets down here, and this is the key part for some of you folks because they think it makes a difference. But anyway, max spherical size is 0.34 inches. Just a little bit bigger than 1/4 of an inch is the biggest solid that impeller, not that one particularly. Actually, it is that one right there. That is a 3410 impeller that's on there. The biggest solid, spherical solid that pump will pass is 0.34, just a little bigger than 1/4 of an inch ball. So that's that information there. So a lot of information already before we get started. And this is going to get jumbled, and if you get lost, stop me and we'll go backwards. But it's important for you to understand how to read this curve so that you know what's going on with the pump that you're operating. Here is a traditional pump curve. This is where that pump's going to operate. So for this example right here, we have 500 gallons a minute at nearly 95 feet ahead. Does that make sense? Okay, so somebody take 95 divided by 2.31. Okay, write that pressure down somewhere. 41.25. Okay. Now over here at this point on this curve, on the same curve, this pump will do 650 gallons a minute. Actually, we'll go the other way. Yeah, 650 gallons a minute at 83 feet ahead, or what is it, 87? Somebody?
88.
So 88. 88 divided by 2.31.
38.09 or 38.10.
Okay. So from 500 gallons to 650, we only got 3 pounds difference, but I'm doing 150 gallons a minute more flow. So I'm doing nearly 35-40% more flow with only 3 pounds difference in the performance. Is that kind of registering, everybody? Mm-hmm. So 3 pounds is not much difference in pressure, but I changed the flow by 150 gallons a minute. Is everybody with me so far still? Now we'll go the other way, and we got 103 feet ahead divided by 2.31, which is roughly 45 pounds.
Yeah, 44 on that.
44, I missed it, damn it. Okay. And then we're going to go out here and do, let's see, 70 feet ahead divided by 2.31 is roughly 30 pounds.
Yeah.
So we have between 800, 4 times as much flow, but we only got 15 pounds differential. See how that pump can move way to the right, way to the left? When we say to the left, we mean we're getting closer to having the discharge pressure valve shut. To the right, we're opening it all the way up and we have no back pressure. So with only 15 pounds, we can either quadruple the flow or cut it by 35, 75%.
And all that is determined by the system. Not by the pump, but by the system. Because remember, this is a pressure creating device. So
If your system changes, your flow and performance is going to change.
Your tank gets full, your head pressure don't change.
And your head pressure's gonna go up. Your head pressure's gonna go up, right? As your tank gets full, you're moving to the left. So it's gonna take longer towards the end of that batch to get it off. Okay? Now if you have no pressure, virtually no pressure, say you only had 30 pounds of pressure, what's gonna happen to the pump?
It's gonna be way at the bottom.
Way over here somewhere, out here in left field. And I'll show you that's not a good place to be either.
Now, when you say the 15 pounds difference to go for, now where's the 15 pounds again? Tell me.
From this point here,
Well, I mean, you're talking line pressure?
yeah, it's system pressure. System pressure. If you change the system by 15 pounds, you're going to quadruple the flow or cut it. So just 15 pounds doesn't seem like much when you're talking about a pump that'll go from 45 to 30.
You could take 15 pounds off the discharge or add 15 to the suction, and it would do the same thing?
Do the same thing, exactly. 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 And you bring up an excellent point. We've been talking all morning about having a system that was open to atmosphere. You could have this pump have 500 pounds of suction. Like if we were talking about an NGL, something that has to be compressed to keep it in a liquid state because it's boiling point. Propane, anything that will boil off at atmosphere. If you opened it up, the tank, it would go to vapor. Anything in that regard. So you could have 500 pounds on the suction side. The pump don't care. Let's back that up. Let's say, because the pumps are not rated for that kind of burst pressure. Let's back it up and say we had 100 pounds of suction pressure. And we were out here, we would have 130 pounds of gauge pressure. Does that make sense? Because we're producing 30 pounds of differential, or delta P, if you will. So from that standpoint, it doesn't care what its inlet is. It's only going to create this amount of pressure because it's a pressure creating device. But know and understand that that pump can move right to left on that curve very rapidly with minute pressure changes. Everybody with me? Because this, I mean, if you're operating a pump and you can't figure out what's going on with it, why it's failing, and you can't read this, it's going to be difficult to troubleshoot and figure out where to go from there. Okay, that was that original line right there, right? That was the full 10-inch impeller. What are these other lines on here?
Different impellers.
Different size pump.
Nope, same pump.
Oh,
Same pump. If you look up here in the right-hand corner, 3410, same pump. Nope, same head. All we did was we have a 10-inch impeller. We went out there to the lathe and we trimmed it to 9, 8, 7, and 6. So we just trimmed the impeller, but you see how we're taking that little bit off of there, off the exterior of it. That's a 10-inch wheel right there. If we trimmed it 1 inch, how that cut our head, our ability for pressure, how it decreased it. Again, it goes back to the same principle. A specific diameter at a specific speed will produce a specific amount of pressure.
You would have to change casings though? I mean,
That's the same casing.
tolerance in there?
That's the same casing. That curve represents the same casing. All we did was trim the impeller. But now,
More of a gap on your water cut?
Yeah.
yes, you're opening up between your cut water. You're opening that up. So there in turn, it probably lowers the efficiency, and we'll get to that in just a minute. Okay, so, but now take whatever it was, 200 or 82 pounds divided by 2.31. About 36 pounds, 37 pounds. 35.49. But we can't even get to 800 now, right? Because it's the end of the curve. If you run it off the end of the curve, bad things happen. It just does, things never come out good. So now we're going to go back to 600 at 60 pounds divided by 2.31 is roughly 25.
What'd you say?
25?
25.97.
Okay. So now we only have 4 pounds difference, right? 4 pounds between 600 gallons a minute and 200. You can change 4 pounds in a system quick, easy. You can triple the flow with just 4 pounds. And this gets even worse when you get into an impeller curve that is flatter. In other words, like a 2 by 1 by 10, 2-inch suction, 1-inch discharge, 10-inch impeller. That curve will look like almost a plateau. There'll be no curve to it at all. It'll just be flat.
What's the purpose of two different sizes?
Flow, performance, head, all those things are going to be. And right over here, if you want to look at it.
4x4 wouldn't do the same thing as a 3x4?
Nope. Nope. All of your ANSI stuff and most of all of your centrifugals are going to have a smaller discharge than they do suction. Because why? We're taking in more volume and squeezing it through a little bitty hole. So then in turn we're increasing the pressure. That's how most centrifugals work. Now on some of your 3x3s, 4x4s, your Gorman Rupp stuff, we're not really trying to create a lot of pressure. We're just trying to get some shit to go through one hole and out the other. Because we'll get a Gorman Rupp impeller and you'll understand. It's only 2 vane. I mean, a 6-inch pump will pass a 3.5-inch spherical solid. It'll pass a softball. Terribly inefficient. We're just trying to get stuff from point A to point B. Really don't care how it gets there. It's ugly. But what we're talking about here is process stuff. And if you look at it, here's a family of curves. All these pumps are represented. We call these families. And this pump will operate in this range at 3,500 RPM. Then you come down here at 1,750 and find the same pump. There it is there. And that gives you a reference point. Back in the old days, this is how we had to work. Somebody called up and said, I want a pump that do 600 gallons a minute at 25 PSI. So you had to go back 25 PSI divided times 2.31 is about 60 pounds. So 60 pounds, we had to go over here, or 60 feet ahead. We had to go over here and find it and get a kind of rough reference point. And then you had to go back and it gets really confusing. But you guys are fortunate. You don't have to do that today. But everybody understands how you can trim the impeller, change the flow and the performance, right? Okay, so next screen gets really confusing. We're going to keep getting squiggly, so hang with me. The BEP, does anybody have a good idea where the BEP is? What is the BEP? What kind of candy do we have in here? Do what? BEP is the best efficiency point. The beep. So if these are all representative of efficiencies, that's what they represent. And this is what we call the eye of the curve, eye of the storm. This part right here, to get the best efficiency, would be right in here. 77% efficient. Okay, so if this is 77% efficient, you see how it kind of moves all the way down? So right in here, as we trim the impeller, is going to be our good. If we're running over here, it's ugly. In other words, we're running at 300 gallons a minute at 105 feet, which is about 45 pounds, right? So what's happening internally in the pump? If we're running all the way over here to the left, what bad effects are we getting in the pump? Could be getting some vibration, but you're probably getting a huge amount of radial load. Remember, we're running close to shutoff. We're pushing down on that impeller. We're loading that inboard bearing, and we are starting to deflect the shaft, right? At near shutoff, okay? So same principle. If we're starting to run out here and we're about to fall off the curve, what's happening? We're getting shaft deflection the other way because we're running against the cutwater, right? So the other thing of it is that when you're running over here, you're getting some axial play. Not a lot, but when you're over here, that impeller is trying to suck right through the front of that pump. When you don't have enough back pressure to keep it on the curve, that impeller is trying to run right out through the front, and that seal face is opening up. Does that make sense? So what I'm trying to get to ultimately is short amount of pressure changes change the effects internally in the pump hugely, quickly. Okay? Everybody with me here on the whole efficiency thing?
Time when you're looking at.
Yeah, if you ever want to get into water to line ratios, things like that, we can, water to line studies, we can help you with that. If there's somebody that's imperative, most time the group of us are not worried about electrical cost, but if you got into a big commercial job or you were on a cooling tower, something that was going to use 75, 100 horsepower, and you pay your bill on electric amps, and that thing was going to run 24 hours a day, 7 days a week, we would start to think about efficiencies and stuff. Smaller 50 horsepower and under, we probably don't worry about it too much on efficiencies as far as electric horsepower. But it is main thing as far as you guys as operators know and understand what's going on in the pump. More lines. What does anybody want to take a guess what these lines are here? Pretty self-explanatory. And then an R, which is required for the pump to operate. To keep this pump from cavitating, we have to have, at this point, 4 feet of NPSH. Why do you think it's less further out here? Because we're not doing as much flow, right? So it doubles when we get out here. It's a lot more important when you're running to the right-hand side of the curve to have plenty of, that's why I said, remember that nominal pipe size, one size bigger? You don't have that friction loss going into the suction side of the pump. Everybody with me still? Where you're pumping fat, which weighs less than water, you have a 0.75 specific gravity. The reason we have to take everything back to head is now with this here would have to be corrected. So in other words, instead of being at 105 feet, we'd have to take that times 0.75 specific gravity. Actually, yours not quite that far. It's 0.9. It'd be 10%. So we'd only be doing 10% as much head because your product that you're pumping is less than water. So that's why we have to take everything back to head. Whereas we're dealing in PD pumps, we don't care. It's a flow creating device. All we got to do is get it from point A to point B. So that is why we don't care in positive displacement pumps what the pressure is. We're going to get it there. Theoretically, if we got enough horsepower, we can put it on the moon. Does that make sense? Because we have so much internal slip internally in the pump, we have to correct it for the specific gravity. Okay, more lines. You ready? Now we got horsepower in there. So if we were over here, see how the horsepower doesn't take many amps, much power to run here? We could get by with depending on whose plant it is, you could probably get by with a 10 horsepower with a service factor of 1.15. Not the way we would normally do it, but it could probably run. But if you were out here, you're going to be tripping out that motor. So on all these curves, you'll see a lot of us, when we quote this, we'll put NOL, non-overloading power. We're going to put enough power into it, enough horsepower, that it will run at any point on this curve without tripping out. The problem with that is, say I spec'd a pump to operate right here. My non-overloading power would be 10 horsepower on this curve, right? I got an 8-inch impeller, my non-overloading horsepower would be right here. Plant changes, management, we want more performance out of that pump. All they got to do is go back, pull the volute, put a 10-inch impeller in it. Oh shit, we're in trouble, we ain't got enough horsepower. I.e. Rose Rock. We can throw stones at them, they're not here. But that'll teach them to skip out on me next time. But anyway, so you understand, and we're not all in the purchasing side of it, but the difference between a 10 horse and a 20 horse is minimal power. I mean, if you're going to buy a 10 horsepower motor, even though you're doubling horsepower, it really doesn't cost that much more. So depending on who's on the front side in the purchasing department, and they're always cutting pennies, they'll squeeze buffalo shit out of a wooden nickel. But we always try to give you plenty of horsepower when we're sizing a pump. So just know and understand that can happen to you. You may have inherited a pump that was trimmed to 8-inch, and maybe they didn't write on the ticket or on the pump that it had an 8-inch impeller in it. All you know is on the label it said 3410. You call and order a 10-inch impeller, put it in there, she trips out every time I turn it on. I mean, it just flips the breaker every time. Know and understand that somebody may not have trimmed it and not wrote it down somewhere. Or puts a 3500 on a 1750.
No, it's 17. The one over there is.
There was one somewhere.
There was one at Hodgman that somebody, or Great Bend or somewhere.
For 3,600 on it, same horsepower.
The same horsepower, but when you change the speed, obviously your velocity energy goes up there and turn your
That was hard.
Hodgman. Okay. I knew it was somewhere because I got a phone call, but anyway. Troubleshooting the pump. And so that you understand, just as a general rule, and I need something to write on, I don't have anything, but if you take that same pump, can we do it? Yeah, we can do it with this one. If you take that same pump at 1750 and you want to know what's going to happen to it if I put a 3500 RPM on it, you square the flow, cube the head, and 8 times the horsepower. So it's a 248 rule. So in other words, you take that same impeller. Am I confusing you some a little bit? I don't want to get overhead, but anyway, you can take that same pump. Let's take a point on the curve, just right there. 400 gallons a minute, 100 feet ahead. That's easy. That's 43.4 pounds, right? So if we take it and same pump, but we're going to put the 3,500 RPM motor on it. Everybody with me? So we're going to go twice the flow. So now we have 800 gallons a minute. 4 times the head. So we're at 40. So we're at nearly 240. 160 pounds of pressure, right? And 8 times the horsepower. We'd have to have 100 horsepower to clear it. And that goes back to the velocity. The faster you turn it, the bigger the wheel, the more energy it takes. You're going to be creating more pressure. It's affinity law. Don't get hung up on it. I'm just trying to get you to understand that as you increase the velocity, you can increase your flow by twice, your head by 4 times, and your horsepower by 8. It's a 248 rule.
So what would happen with that 3,600? The flow wouldn't keep up to feed the pump?
Well, now guess what happens to your NPSH?
You're right.
You're exactly right. You're on the right track. Your NPSH went off the chart. So now you're 3 times what your NPSH requirements are. You're nearly at 27 feet out here. So you're exactly right. But a lot of people don't think about that. I'll just put this bigger. I got the same pump and everything in there. I don't want to change all the plumbing that it may require, but I need twice the flow. And I know that if I have twice the flow, my friction loss to get the fluid through the pipe is going to exponentially double. I'm going to put twice the flow in it, so that my pressure's going to go way up really quick. That's all right. Hell, I can buy 100 horsepower motors every day. So I just stick that on there. But they always forget that they may not be able physically possibly to get it into the pump. So, very good point.
Will that do the same thing if you change the vanes?
Yeah, you start adding vanes or decreasing vanes. Yeah, you increase the velocity or decrease the velocity. Same principle. Like the Gorman-Rupp, we'll go out and if you guys want to, we'll get a Gorman-Rupp impeller and I'll show you. It just has 2 vanes. Terribly inefficient, nasty looking old rough castings. They're just designed from point A to point B. What is exact? Probably your Jaegers and MPs and Flowmaxes and stuff like that really doesn't have a finished casting to it as much as they're just trying to get stuff from point A to point B. Transfer pump. It's not a true process pump.
And with that same note on the Gorman-Rupp, you look at a Gorman-Rupp curve, it's going to have, instead of trimming the impeller, it's going to have speed differences.
because most of those are belt drive.
Yeah, they're belt drive, so it's gonna have, 1760, 1500, and it's gonna start going down in speed. And so, but it's the same, you're looking at the same thing, they're doing the same thing, they're just slowing the impeller down. And they're creating different curves by slowing the impeller.
Yeah, you slow it down, you get pump less.
There you go, exactly. And you're going to have less head.
Less hit.
You're doing the same. It would be, if you're at 1800, you might have a 10-inch. The next one might be 1600 at the 9, and so on and so forth. Now, when it gets really confusing is when you throw in, not confusing, but you throw in a variable speed, a potentiometer pot. Some of you have them in the plants and so on and so forth, and they're great, fantastic tool, because you may want to set, you may only want pressure. Because your pressure's changing in the plant, your system's going up and down, for instance, in an apartment building. Everybody gets up in the morning to take a shower, it's going to take a lot of water. So we're going to increase the pressure, right? Everybody goes out and walk up at 10 o'clock, but you still need 40 pounds of pressure on the 4th floor. Pump slows down. You're reading that 4 to 20 signal off that pressure transducer. So variable speeds, great things for centrifugal pumps. As far as that goes, variable speeds are great for any application most of the time.